So this will be the solution video for Physics Paper 3 from May 2018, Time Zone 2. And we're looking at Section A only, not the optional topics. And so here's Section A, number 1. We're talking about dropping a ball to determine the acceleration due to gravity. Things that we know, we said we have it's a metal sphere. It's dropped from rest, and we measure the time is measured, and then we also know some other things. We know the diameter of the metal sphere. That's given right here, diameter. We know the distance between the point of release, which is up here, and the trapdoor itself, which is down here. That's given. And then we measure the time for fall. That's also given. And so number 1A wants to know what is the distance fallen in meters by the center of mass of the sphere from where it's released down to the trapdoor. Okay, so to find the distance fallen, we first have to recognize that the point of release is the top of the sphere and the trapdoor is at the bottom of the sphere. And so the distance is from the point of release to the trapdoor. That is 654 plus or minus 2 millimeters. But the question specifically says, what about the center of mass, which is really what we're concerned with. On any rigid object, we want to know about the center of mass. And so the center of mass, if you look at my line that I'm drawing there, that's actually the center of mass. So to kind of like redraw this, all right, so that's what we're talking about, but really what they're asking in 1A is this. So there you go. But if you look at the diagram, really it's the 654 plus or minus 2 millimeters, plus you're missing half the diameter on both ends. So if it's half the diameter on both ends, really what they're asking for is the distance from point of release to the trapdoor minus the diameter of the ball, and they give us the diameter of the ball. All right, so we figured out that much. Then we need to do the math. But again, see, this is 2 points. I think maybe it should have been 3 because we had to figure that out. And then if you read carefully, it says in meters, whereas the diameter and the distance are given in millimeters. So of course, we're going to need to convert. All right, so then as I subtract 0.654, as I subtract 0.0120 from 0.654, I get 0.642. And remember, when you're subtracting with significant figures, you have to go with the number that has the least number of significant figures after the decimal point. And 0.654 has 3 sig figs after the decimal. 0.0120 has 4 significant figures after the decimal. I have to go with 3 sig figs after the decimal. That leaves me with 0.642. All right. Now, the absolute uncertainty, whether adding or subtracting, you have to add absolute uncertainty. And so this 0.002 and 0.0001, when you add the two of those together, you get 0.0021. Now, notice that not only is that 2 digits of uncertainty, that uncertainty is also more precise than the measurement, which is not allowed. So my final answer is 0.642 plus or minus 0.002 meters. You can also write that in scientific notation. That would be 6.42 times 10 to the negative 6.42 plus or minus 2. Hold on a second. No, scratch that. It'd be 6. Why am I saying it? Let me just write it. Other ways of writing it. 6.42 plus or minus 0.002 times 10 to the negative 1 meters, or 642 plus or minus 2 times 10 to the negative 3 meters. Anyway, let's move on. Oh, one other thing. What are the 2 points for? The first point is for actually finding the distance of the center of mass. The second point is for the absolute uncertainty. They could have included more points for more details. There was actually, the mark scheme has a lot of wiggle room in this particular question because they only assign 2 points to it. For what it's worth, before we move on, they would actually accept this answer right here, which to me is a travesty because that has absolute uncertainty that is more precise than the original measurement, which is a no-no. But I think that to be kind, they actually said, all right, you got that far, good enough. All right. And we have ourselves an equation for acceleration due to gravity, and we are going to calculate acceleration due to gravity while also processing the uncertainty. So it's kind of similar to the previous question. Let's go. All right, 2 times the distance to the center of mass over the time to fall squared. Oh snap, all this time I'm using D for distance and displacement. I should have been using S. That's my bad. You're just gonna have to forgive me. Yeah, I'll fix it later. I'm gonna be consistent with my variables right now. In writing the equation and filling it out, I reached back to collect the data, so the measured time for fall, 0.363 plus or minus 0.002 seconds, and that number is squared. Okay, so first of all, 2 times the distance to the center of mass. 2 is an absolute number. There's no uncertainty on just the number 2. So you would double the distance and you would double the absolute uncertainty. Now, this is interesting because you're doubling the distance, which means you would double the absolute uncertainty, but you're squaring the time. When you square something, you're multiplying it times itself. So we don't double the we don't double the absolute uncertainty, we're going to need to double the percentage uncertainty. So let's actually get a percentage uncertainty on that 0.363. And actually, come to think of it, I'm going to need the percentage uncertainty on the distance of center of mass anyway, because I'm going to be dividing that by time squared. So when I divide, I need to work with percentage uncertainty. Now, the denominator is squared, so since it's squared, we multiply the percentage uncertainty times 2. So when you raise a number to a power, you multiply the percentage uncertainty times that power. That's what we get after we square the t. Then we divide the 2 times the distance by t squared. And so in dividing, we add the percentage uncertainties. So dividing the 1.284 by 0.131769, we get an acceleration due to gravity of 9.74 and change meters per second squared. Adding the percentage uncertainties, it gets us 9.74, etc., plus or minus 1.41346%. Then we need to convert the percent back to absolute uncertainty, because that's what they asked for. And then when we control for significant figures, the original numbers were both to 3 significant figures, so that would get me 9.74 plus or minus 0.14 meters per second squared, or you can do 9.74 plus or minus 0.1 meters per second squared. Something along those lines will work. By the way, this is a 4-pointer, and so the first point is actually finding the value of g using the equation. The second point is finding the percentage uncertainties here and here. That's points to 2 and 3, and then the last point is getting the final percentage uncertainty on g. Okay, let's proceed. That was it for number 1, so now we're on to number 2. Okay, so we have this light source with a cover, and it gives the diameter, the radius of the cover as capital C, and the distance from the edge of the cover to the light sensor as x, and it says that the intensity of the light is capital I, and the power coming out of, it says the radiation coming out of the lamp has a constant power P. And so we have the relationship between intensity and distance between the cover and the light sensor. That's I equals P over 4 pi in parentheses C plus X all squared. And then you can also rewrite that as 1 over radical intensity is some constant times X plus some constant times C. And so basically using those two expressions, they want you to show that the constant, I'm assuming that's constant. Does it say K? K is a constant? Yeah, I mean, that's usually what that means. Show that the constant is 2 times radical pi over the power P. So first, from the second expression, I'm going to try and get I by itself so that I can then relate the two expressions. I can equal them to each other. So that's what I did in these steps here. I got rid of the 1 over radical I. That's what I did right there. And then I combined the x and the c because I'm trying to get, you know, something that's C plus X over there. So I did that here. I'm trying to get rid of the radical I, so I squared both sides. And that's what I did here. And now I have I by itself. So now that I have that, I can relate it to this expression up here and set them equal to each other. And you can see from the denominator on both sides of the expression, I have c plus x squared. So that's where the c, that's why it's no longer in here, because the c plus x gets canceled. And we're left with p over 4 pi is 1 over k squared. Now I'm trying to get k by itself, so I can really just invert both sides of the expression, and I can say k squared is equal to 4 pi over p. And just, you know, inverted both sides. Cross multiply, I guess you could do that too. And so I'm trying to solve for k by itself, so I take the square root of both sides of the expression, leaving me with the constant equal to radical 4 pi over p. Radical 4, square root of 4, of course, is 2. So when I take radical 4 out of the expression and put it as 2, I get, ta-da, k is 2 radical pi over the power. Man, that's 1 point. Sheesh. All right, let's go with number 2b. Just as a side note about careful reading, I just want to say that I just recorded a good at least 10 minutes of this solution, and then I went back and deleted it because I got lost because there was an error that I couldn't find. And I was banging my head against the desk over and over, and when I realized that what happened in the end is that I missed this meter. Because later I was like, now wait a minute, intensity, power's in watts, but intensity is watts per meter squared. And so actually I missed that M right there, which of course is an issue. So as always, look and read carefully. And just as another side note, based on what I just said, I was like, wait a minute, didn't you just finish saying that intensity is power per unit area? Wouldn't area be in meters squared? And that's exactly what it is here. Intensity is power, and then you can see right here x displacement, but it's squared, so that would refer to the area. And then when you isolate, when you do 1 over radical I, that's when you get rid of the x squared over here. This of course follows the inverse square relationship of the intensity of light with distance, but technically you don't need to know that in order to answer this question. Anyway, that's just enough of my little side notes. Let's actually get on with this question. Okay, let's cut to the chase. So here we have a graph of 1 over radical intensity with units of watts to the negative 1/2 times meters. And the data is a little bit wonky, but it is the experimenter, I should say, has drawn a line indicating linear proportionality. And let's go back for a second and actually look at the expression from the previous page talking about 1 over radical I. And here it is. So we have 1 over radical I is some constant times x plus the same constant times c, which is not, I mean, I suppose it is a constant, but it's a defined constant being the radius of the cover around the light source. And I've been thinking about this, and it's like, what even is the point of the cover, especially when I say that all of the radiation is transmitted through the cover? And I think it's just simply that the actual source of the light is considered to be a point source, which for the intent of this experiment, like kind of is a point source of light, but there's some cover on it. You know, we're talking about a bulb here, right? And if you actually were a student experimenter, you would have a cover over your filament or LED or whatever, and so you would need to account for the size of that cover. And so the radius of the cover is given by C. I think that's fully appropriate. And this is not just me like kind of hemming and hawing. This is like something that, you know, again, paper 3 part A is all about, you know, experimental design and processing, so that's something you definitely need to consider. So again, just for what it's worth, the original expression up here is that the intensity is inversely proportional to the square of the displacement, which again makes sense following inverse square law for light, which again, we're going to pretend like we don't know that because you don't actually need to know the physics. But if you actually wanted to take that 1 over x squared, that inverse square law, and turn it into something that is a linear expression with displacement kind of right here, then you would need to do 1 over radical I, and that's why they did that on that side here. And I just want to comment on the units of watts to the negative 1/2 times meters, and that's fully an artifact of 1 over radical I, where I is the intensity. The units for intensity are watts per square meter. So if you do 1 over the square root of intensity, you wind up with units of watts to the negative 1/2 times meters. So here we have BI, where they want us to estimate C. Well, let's revisit the expression in which C exists. So it's in 2 of these. The first guy here, I need ink here, but also since I'm looking at a y-axis of 1 over radical I, I'm really more concerned with this guy right here, and so I'm looking at this C constant, which would be, again, the radius of the cover around a point light source. Now, my first thought, when I first approached this, and I think I said earlier that I deleted half the video because I missed a unit on the y-axis, but my first thought was that this expression here follows the equation of a line. That's why, even though the data doesn't look terribly linear, it is in fact a linear relationship, not necessarily directly proportional, but simply linear. And if we go back to this equation here, this guy, I can show you why it's linear. Here's our classic equation of a line: y equals slope times x plus b, y equals mx plus b. Why m is slope, I have no idea, but I'm not going to waste time on that. But now y is 1 over radical I y, and if we look right here, we can see 1 over radical y is in fact the y-axis. And so we can actually, if we're trying to figure out what c is, we can see that from this expression that the y-intercept b is equal to some constant times c. And it's like, well, what is that constant? That constant reappears right here as the slope. So you can actually take the gradient of that line, 2-point slope on that line, and you can figure out what that slope is, figuring out what k is, and then figure out what the y-intercept is if you were to extrapolate it and see what the y-intercept is. That's a hot mess. I'm just trying to prove a point here. And so from the graph, I can determine k, which is the, wrong pen, which is the slope. I can figure out what b is off of the graph, and knowing b and k, I can solve for c. But actually, there's a quicker way of determining c, and I checked the mark scheme, and they make reference to the x-intercept, which I find very interesting. To find the x-intercept, we're going to have to extrapolate the line. In other words, extend it. Now, this line, of course, has a y-intercept right about here, but it also has an x-intercept right down here. And the mark scheme made reference to the x-intercept, and I was like, it's not something you see very often, so let's explore that. Because we talk about y-intercept and equation of a line over and over, but x-intercept is not something that we come across that often, so let's see what that can do for us. Okay, yes, very good. We've established that this expression does, in fact, hew to the equation of a line, but right now I want to look at explore x-intercept. And the definition of the x-intercept is when y equals 0, which, of course, the y-intercept is when x equals 0. Let's take a look at the graph. Like, yeah, y-intercept right there obviously is where x is equal to 0, but if you keep your line going back, and this is also why they actually show the -5 and they keep on going backwards, that x-intercept is in fact where y equals 0. And it's like, well, why would we care about the x-intercept? Well, y is 1 over radical I, so if you can set the left side of the equation simply to 0, and if you're trying to solve for c, watch this. So I'm writing notes over here, but naturally when you're answering a question, nothing gets counted unless it's in the box. So let's go to the box. Let's go down to the box. You need to make those sound effects. Okay. And again, to be clear, you might say like, hey, wait a minute. How come we could just say 1 over radical I is equal to 0? We can just do that? Well, yeah, if we're trying to establish what the x-intercept is, we can in fact do that. That's the whole definition of the x-intercept when y equals 0. So let's find out what the x value is in that case. We can check the graph for that. Based on my read of this, I see that the x-intercept when y equals 0, x is negative 3.5. But since we're solving for c, then let's isolate c first and then put in the negative 3.5. So I just subtracted the kx to the left side, and I divided both sides by k, and I wind up with negative x is equal to this constant, this radius of the cover of c. So, like I said, when y equals 0, x equals negative 3.5. So I slip that in, and negative of negative is a positive, so therefore that radius of the cover is 3.5 centimeters, since x is provided in centimeters. Again, would my original attack have worked in terms of fitting it to the equation of a line? Yes, except that I've yet to see a problem that makes use of the x-intercept instead of the y-intercept, and especially since it's considered, it's top line, it's the first solution in the mark scheme. I think that it's one of those techniques in terms of manipulating graphs that stands to be good, has worth to be mentioned, I should say. Stands to be mentioned, that's what I was trying to say. I'm sorry, it's 10:15 at night. I'm having trouble finding words. And just to be clear, in case you think HESSEL's off his rocker and this is a waste of your time, the mark scheme says that acceptable values are between 3 and 4.5, so my 3.5 centimeters is within range. And the 2 points for this question to be found, one is the recognition of the use of the x-intercept, the second is the actual answer. Okay, so there is C. And then it says find P to the correct number of significant figures. All right, one final comment about this particular graph is I was like kind of going on about the x-intercept, but it's kind of like, what is the deal with that, and why is the x-intercept even negative anyway? And it's the reason why is because when they started measuring, they start measuring from the edge of the cover, right? So then that's actually, they call that 0 and go from there, but the edge of the cover is not actually at the light source. So we can see that when x equals 0, there is some intensity to the light. And or rather the intensity has actually already started to dim, because what's happening here, we know that as displacement increases, the intensity drops, like with the square of the displacement. Well, I know that. You may not know that, and you actually don't need to know that to answer this problem, but I just want to explain something about this negative x-intercept. And so it's very important to realize that the y-axis is 1 over radical intensity, and even just ignoring the radical right now, just the fact that it's 1 over, meaning that as the displacement increases, 1 over the intensity increases because the intensity actually decreases with displacement, but if you take the reciprocal, you take the inverse of it, then it would actually have a increasing trend, which is what we see. But what happens in that case is that as you get closer to the lamp, like the closer you get to the lamp, the intensity is going to get bigger. So this x-intercept back here is actually the point of the lamp itself, where it has the maximum intensity, where 1 over the intensity would therefore be 0. And then the actual 0 point of the displacement of that distance or displacement, whatever, from the cover, that's actually the cover edge. That's not really where the source starts. So that's actually why this graph actually goes back into the negative displacement, which you would say like doesn't really make sense, except that it does, because they start measuring from not the point of the light source here, but they actually start from here, the edge of the cover. All right, that's enough of that. We got to move on. This is taking far too long. And apologies if I was just like a slurring mess last night. I was tired. But my solution is correct here. 3.5 centimeters for the radius of the cover is legit. All right, so let's move on. In the problem, it's given that k is 2 radical pi over the power. So if we're going to solve for the power, we're going to get it alone, divide both sides by 2, square both sides to get rid of the radical, and then invert to put p into the numerator. So then the power is 4 pi over k squared, which would be really neat if we knew what k was. We don't, but we can find it. We're also given this expression, 1 over radical I equals kx plus kc, which is actually fits the equation of a line. So let's take a look at the graph. We see our graph is 1 over radical I on the y-axis, and then distance from the cover of the lamp is given as x. So we can see that 1 over radical I is y, k is the slope, and k times c is the y-intercept. Now the guide, the mark scheme, says that, yeah, you can go and grab a single point for 1 over radical I, and knowing c, and like for instance, we could use a single point getting an x value and a y value, and then just plugging that into the equation, and knowing c, we can solve for k. That's worth 3 out of 4 points. I don't really know why. I think what they really want you to do here is go after the slope. I would argue it's probably faster anyway, so if you just go and solve for the gradient, that's equal to k, and I can bring that back into the p expression. Remember that the IB is very picky about this. When you take a 2-point slope, the points must be well separated. They actually specify in the mark scheme that the 2 points must be at least 10 centimeters apart. That's as in the x-axis, not literally 10 centimeters on the paper. Also, one other thing, I took this opportunity to convert from centimeters to meters, so that we're all working with the same basic units. Because watts assumes meters, it does not assume centimeters. So I have meters over here and centimeters over here, so that we have common units. I converted from centimeters to meters. And so my slope is 125 watts to the negative 1/2. The meters on that y-axis, this is its watts to the negative 1/2 times meters, cancels with the meters in the denominator for the slope calculation. Yes, I recognize that 125 is not the right number of sig figs. I'm going to control for sig figs at the very end. And there we have it. The power is 8 times 10 to the negative 4 watts. Mark scheme says anywhere from 6.9 to 9.5 times 10 to the negative 4 is acceptable. The weirdo watts to the negative 1/2 get resolved, but with on the bottom of this with the 125 squared in the denominator, so that puts watts back into the numerator and gets rid of the negative 1/2. So we have 8 times 10 to the negative 4 watts for our final answer. And it's 8.0 based on the significant figures in the slope calculation. Okay, so C says, why would graphing intensity versus 1 over x squared, how would that make the analysis in BI and BII harder? Well, here's the formula for I relating to x squared and to power. And again, it's a constant power, but it's so that's also a constant. So really it's a graph of intensity versus intensity is a function of 1 over x squared, because everything else is a constant. So yeah, if they tried to graph intensity versus 1 over x squared, they would get themselves a curve. And then that curve can be analyzed to figure out the values of k and c, especially the constant k. But that's going to be a real toughie. You're better off this is why we linearize. It's the whole point. Because once you linearize, then you can do things like find the x-intercept and the y-intercept and the slope, which is how we found k. So yeah, it's not impossible, but it would be a heck of a lot more difficult. And those are the 2 points for that question. One is recognizing that I versus 1 over x squared is a curve. And then the second point is, so therefore it would be difficult to find k and c and then figure out what the actual power is, because in order to figure out the power, you got to figure out what k is. And that's that. All right, thanks.